All righty, folks. How we all doing today? It is a little early. Got a little bit of a bright light there in the background. That's all right though. Glad you guys could be here today, and we are going to take a look at our next thing that we are dealing with here on chapter 8. So we're going to be looking at we did arithmetic sequences in series last time. Now we're going to look at something called geometric sequences in series. And again, we got introduced to this a couple days ago. But just want to kind of take a little look at it in general. And again, just like arithmetic sequences are really closely related to geometric, I'm sorry, arithmetic is close to linear, geometric is close to exponential functions. And here's what I mean by that. So first of all, just like before, we had an initial value, right? So there's our initial value. Well, that initial value on an exponential function, when we were back in integrated 1, we call that the y-intercept. So they both are going to have that same idea kind of working out there. Same idea. And then they both have this idea of some sort of, whoopsies, wrong one. There we go. They both have something that's in parentheses taken to an exponent. For a geometric sequence, we call that a common ratio. Well, in exponential functions, we call that a multiplier. So again, those will be related. Really, all we need to remember here is that the common ratio and the multiplier, they are essentially the exact same thing. All right, there's nothing different about them. So if I wanted to find if we look at this first problem, if I wanted to find that initial term, all I'm really asking you guys to do is when you plug 1 in, what do you get? So if I plug 1 into my equation, if I plug it into my sequence rule, what value would I get? So 1 minus 1 is 0, and anything to the 1/3 power. So we have 7 times 1/3 to the 0 power. And anything to the 0 power, well, that's just 1. So we have 7 times 1. That means our initial term would be 7. So again, you can kind of see here a little bit how the initial term is the number out in front. The common ratios, that's that number that's the repeated multiplier. So that's going to be the thing that is in our parentheses. So this right here, we would say that that is our common ratio. So that will be our common ratio. All right, folks. So what we're going to do today is we're going to just kind of play with this idea of geometric sequences in series and see if we can get a little bit more familiar with them as we go through. So let's take a look at a couple of them here. So let's list the first 5 terms. I don't know why that's still on there. Let's just get rid of that. You have the first 4 terms. You could probably get the next one if we can figure out the rule. So we don't need that there. We'll just get rid of it. Anyways, it says determine the geometric rule. So we have to go through and ask ourselves, well, how do we go from the second term to the first term? And if it's geometric, and we're told it's geometric, that means I should take the second term and divide it by the first term to figure out what r is. So if I take 1/3 divided by 1/6, well, that's the same thing as 1/3 times 6/1. So 6/3, that would be 2. So apparently, it looks like that if I were to take this and multiply by 2, I'd go from 1/6 to 1/3. If we do it again, 1/3 to 2/3, so again, that's just multiplying by 2 as well. And 2/3 to 4/3, it is actually multiplying by 2. So our r value really is 2. This right here, the very first thing we see there, the 1/6, that is our initial value. So a sub 1 would be 1/6. So if I'm writing the geometric sequence for this, the geometric rule, I'm going to be doing a sub n is going to be equal to 1/6, that was the initial term, times 2, that's the common ratio, to the n minus 1. Oh, I hear one of my kids waking up in the background. Might get some more light coming in here eventually. All right, now if I want to find the 11th term in the sequence, all we're doing is just taking our 11 and plugging it in. So 1/6 times 2 to the 11 minus 1. And you guys plug that into your calculadoras. And if you did, you would end up finding out that it equals either 512 over 3. Clearly, I did that in my head. Or maybe not. Or if you wanted to, you could call that 170 2/3. All right, friends. Well, let's have you guys try it. Take a look at this and see what you guys can do with this next one. Cool. All right, now you've unpaused the video. Let's try to take a look here. All right, so if I want to figure out what that R value is I'm multiplying by, if I know it's geometric, my common ratio is going to be whatever my second term is divided by my first term. Well, in this case, it does look like it might be a fraction. So if I were to simplify that, I would end up with 1/3. So it looks like I'm multiplying by 1/3 all the way through. And again, multiplying by 1/3 is the same thing as dividing by 3. But we only do repeated multiplication with geometric sequences, so we're going to leave that division for something else. No, we won't actually even touch it. So we're multiplying by 1/3 here. It is going to be, that is the R value. You can see that kind of come up. And now we got to go ahead and get our A value. So again, the A value is always the initial term, not the thing I wanted to. So that means our A value is 1/62. (162), not 1/62. So our first term is 162. So now we have our common ratio and we have our first term and we plug it in. So A sub n equals 162 times 1/3 to the n minus 1. So there's our geometric rule. And we want to find the 12th term. So we're going to take it and we're going to plug in 12 in for n. And when you do all that, you find out that the 12th term would be equal to 2187. All right, so there we go. Now let's keep going here, friends. What if I give you something like this? I tell you what the second term is, and I tell you the fifth term, and then I want to know the geometric rule. Well, that's kind of a weird one, isn't it? Let's see here. Let's see if we can't try to figure this out here. I'm going to draw myself a little table. Sometimes I find that tables kind of help. It might not help you. I'm hoping it will help me out a little bit. So here's what I see. I'm dealing with term numbers, and I'm looking for the A sub n value. So I don't know every value in my term. I need to eventually know them all, but I don't. So what I do know is this. I know the second term is 6. So I can go in here, and the second term I know it would be 6. I know that my fifth term is 48. What I don't know here, friends, is what the ratio is that gets me there. So if I think about it, on a geometric sequence, I can multiply by r to get from my second term to my third term. I can multiply by r again to get from my third term to my fourth term. I can multiply by r again to get from my fourth term to my fifth term. And so all of a sudden I'm looking at it. If I were to take 6 and I multiply it by r 3 times, I would be equal to 48. So in other words, 6 times r cubed is 48. So if I divide both sides by 6, I get r cubed equals 8, which means when I take the cube root, r is 2. That's one way to do it. You could do this also with using our little formula here to figure out 2 values and go from there. So that could have also been done that way as well. And here's how it would have worked here. If you wanted to use the geometric equation for it, I'm more of a visual guy, which is why I kind of break it up that way. But a sub 2, 6 times a1 times r to the 2 minus 1, which would have been 6 equals a sub 1 times r to the first. And we could have done the other one as well. 48 equals a sub 1 times r to the 5 minus 1. So 48 equals a sub 1 times r to the 4. So if I were to take that equation right there, and you'll see how they end up giving you eventually the same one. So guys, I don't care if you use the table or if you use an equation, totally okay with that. But I see that this right here has a sub 1 r to the first. So I could break this up as 48 equals a sub 1 times r to the first times r cubed. If we do that, this a sub 1 r to the first, that would actually be 6. So again, if you want to use an equation for it, you can use the equations. I'm more of a visual guy, so I tend to go more with the table and what I showed you guys the first time. But either way works. You guys take your pick. All right. We're all different friends and different folks out there. So you guys go ahead and figure out what works best for you. Either way, you still end up getting r equals 2. So I'm going to come back here. Found out that r was 2. And if I know that r is 2, that means I'm multiplying by 2 every single time. So if I want that first value, that means I have to go backwards, and I'm looking at what multiplies by 2. What number times 2 would give me 6? In that case, I would end up finding out that my first value, my first term would be 3. Well, that would be my a sub 1 value. So a sub 1 equals 3. And we could, if we were to go through and do that with the equation, it would look like this. So 48, divided by 6, 8 equals r cubed, 2 equals r. And once you know what that is, we can come back and we can figure out what a sub 1 is by plugging it back in. 3 is a sub 1. So whether you use a table or you use an equation, it's really on you, friends. You deal with whatever makes the most sense to you. Again, I'm more of a table guy, but hey, if I'm dealing with big numbers that are out there, I probably would use the equation. So 3 times 2 to the n minus 1. Now we have our 8th term. So 3 times 2 to the 8 minus 1. So we're going to go ahead, we plug that into our calculators, and friends, we find out that the 8th term is 384. All right, so we've played with some sequence rules and sequences a little bit. Let's deal with some summations here. Now we can have a sum of a finite series. That means we have an n value, or we can have a sum of an infinite series. Now the n value is going to play a piece in this one. Notice how we have the n value there. And remember that n is still going to be the upper number. So let's just write it out. Upper limit minus the lower limit. Once you've done that, add 1. So n is still going to be the upper limit minus the lower limit plus 1. All right, so let's see what we got here. We're going to be using this. So the first thing we always do is we look here and we say, if this is infinity, we're going to use the infinite sum. But if it's a number, then we're going to be using our finite. Well, this is 5, so it is finite. So that means I need to figure out what n is. So n is 5 minus 1 plus 1. So I am going to have 5 terms here. And we need to know what the first term is. The first term in this particular sequence. So I'm going to take my 1, since that was my lower bound. I'm going to plug, or my lower limit, I'm going to plug that in. So 1 minus 1. So a sub 1 is 3. So we're going to now use our formula. So a sub 1, so 3 times 1 minus, oh, got to come back, put the r in here in a second. 5 all over 1 minus r. So we got to get, now we got to go back and see what r is. And r is always whatever number is in parentheses with the exponent. So r is 2. So if we plug in all our values in here, if we were to go figure out all 5 values and plug them in, they would equal to whatever this equation would be. So 10, nope, wrong value. Little precursor, that might be the answer to the second one. It would be 93. All right, friends, why don't you guys pause the video and see if you can't try the second one and see how you do. All right, let's go for it. So now if I'm looking at it here, I have n equals 7 minus 1 plus 1. So n is 7. Plug in our lower value here to get my first term. So 3 times 1 minus 1. So that means it's our first term is 1. And if you look at it, it might kind of make sense a little bit. That means that this 3 technically could have been in parentheses and the number 1 would have been out front. So 1 is our a sub 1 value. So I have 1 times 1 minus, I've got to figure out that parenthesis here in a second. And I had 7 terms. And again, the r value is whatever is in parentheses, friends. So r equals 3. So we plug that in there. And we are going to crank it out. And that final answer would be on that one. Here's our 1093. All right, why don't you pause the video and try this last one, and then we'll see what we can do with it. All right, here we go. So n, 6 minus 3 plus 1. That means there's going to be 4 terms in this sequence. My initial value for this sequence, not overall, but just for this sequence, is when I'm dealing with 3. So a sub 3. So that'd be negative 2 times 2 to the 3 minus 1. So a sub 3 is negative 8. So we plug our values in here. We have -8 times 1 minus whatever the R value is. And I had 4 terms. So 1 minus, these are all finite series. So the R is going to be whatever's in the parentheses. So R is 2. And that fun answer, friends, would be a -120. Well, we did some fun with finite. I guess we probably should play with infinite a little bit, huh? All right, let's try one together. Then I'm going to have you guys try one here. All right. Well, let's remember what the formula is. Let me see if I can't write that back up on top here so we know what we're dealing with. So we have, if it's infinite, we said it was a sub 1, 1 minus r. So this is an infinite geometric sum. Infinite geometric sum. And so, again, real easy to tell, friends, we're dealing with infinity. You just look at the top bound. If it is an infinite sign, well, that means it's an infinite sum. So we just got to know a couple things here. We got to know what the R value is, and we need to know what our first term is. So to get the first term, or essentially whatever that lower bound is, so a sub 1, we plug it in here. So we have 35 times 1/5, 1 minus 1. So a to the first would be 35. So the sum of our first 35 terms, we have 35 on top. Oh, sum of our infinite number of terms. So I guess I don't even need to put it in there. So we have 35 over 1 minus whatever the R value is. Now, we got to remember a couple things about the R value. First up, if you notice here, if you put R as infinity in the denominator, well, that would be bad, friends. Okay, R can't be infinity. So, or not infinity. R can't be 0. If we put 0 in, holy wow, early morning. Can't plug 1 in. If I plug 1 in, if I have a radius that's 1, then I would have a value that wouldn't work. So our radius, our R value, if it's an infinite series, R can never be 1. Now, for an infinite, if R is greater than 1, the absolute value of R is greater than 1, that means our sum is either going to be positive infinity, or the sum could be equal to, and by the way, I should never put equals infinity, because friends, you can't ever reach infinity. Only Buzz Lightyear can. And he went beyond, but that's another story. All right. So we're not going to be dealing with a R value that's greater than 1. We definitely cannot use an R value that equals 1. Doesn't work. Okay, that would just be that would not be a geometric series, honestly. What we are going to focus on is when our R value is less than 1. So that's the one that we want right here. We want this one right here. When R is less than 1. This is like our big giant window. So if you notice on this problem, our R value is less than 1. Those are the ones that we care most about. So we're going to plug that in here. And we're going to solve it. So you can either solve it by putting in your calculator, or these aren't bad to do at all. So 1 minus 1/5 is 4/5. It's just a complex fraction, which we've already played with a little bit. Multiply by 5, that's my lowest common denominator. So multiply the top by 5. Really, that bottom 5 kind of look like a 6 to me, I'll tell you what. And it turns out that infinite sum, if we were to add up all infinite values, it would be equal to 175 over 4. I think that's crazy, friends, that I can add an infinite number of things together and it goes to a value. That's called converge. It converges on that value. Diverges means it goes off into infinity or negative infinity. Might have a movie or a book series or something about this idea of convergence and divergence. But we're not going to get into that idea too terribly much now. We're just going to kind of keep moving through. But friends, why don't you guys go ahead and pause the video and see if you guys can deal with this next one here. How would you find this infinite sum? All right, let's see how you did. Plug in our 1. So 7/10, 1/10, 1 minus 1. So that first term would be 7/10. So if I want to find the sum, I'm going to plug it in here. One minus, and let's see if we can figure out the R value that it goes with. That'd be the thing inside the parentheses. So R is 1/10. So we'll plug that in here. All right, and if we clean this up a little bit, friends, it looks like I have 7/10 over 9/10, which would be equal to 7/9. You know, the weird thing about that, friends, is I know that 7/9 is the same thing as 0.7 repeating. 7, 7, 7, 7, 7, 7, 7. But now I'm noticing that 7/9 is the same thing as an infinite geometric sum. So somehow it looks like a repeating decimal then is actually equal to an infinite geometric sum. This is going to be the last thing that we play with here today. If this is the case, that means I should be able to use a geometric sum to write any repeating decimal as a fraction. And that's going to be literally, honestly, what we do here at the end. How do we rewrite 0.21 as a fraction? So first of all, let's take a look at what 0.21 is. 0.21 is the same thing as, or 0.21 repeating would be the same thing as 0.21212121. You kind of get the idea, right? It kind of goes on forever. So that means that 0.21 repeating, I could probably write that then as 0.21 plus 0.0021 plus 0.000021 plus 0.00000. You kind of get the idea, right, friends? All right. Plus, and we keep going on forever. So this 0.21 repeating. If I wanted to write that as a fraction, let's see here, 0.21 would be the same thing as 21 over 100. And however many numbers are after the decimal, that's how many zeros I have. So 21 over 10,000. This next one has 6 numbers after decimal, so that'd be 21 over, was that, 1,000,000? That's a lot of zeros. And then this next one would be over 100 million. So if I take a look at this, I think I can actually figure out maybe a pattern that's going on here. I see 21 over 100 to the first. I see 21 over 100 to the second. I see 21 over 100 to the third. And I see 21 over 100 to the fourth. So friends, I believe I can write this then as a infinite geometric series, or as a summation. I think this is the same thing as n I to the first 21 over 100 to the nth power. Or another way to think of it, and probably a better way to think of it would be this. Probably an easier way for us to be able to see what that geometric series would actually be. Well, friends, why don't you guys go ahead and pause the video here and see if you guys can figure out what would be the summation for this series. All right, here we go. Let's see how you did. If I plug my first term in there, 21 times 1 over 100 to the first. And I got to tell you, I probably should give you an idea here. Whatever the repeating number is, whatever the repeating digits are, when you do these, that's always going to be your a sub 1. And however many numbers repeat, in this case we had 2 numbers repeat, therefore the common ratio always would have been 100. If there was one number that repeats, it would have been 1 over 10. If there were 3 numbers that repeat, it would have been 1 over 1,000. So it gives you an idea kind of how this works. So R is 1 over 100. So if I wanted to deal with my sum, I'd get S equals 21 over 100, so the first 2 decimals, 1 minus the rate. So we have 21 over 100, 99 over 100. Oopsie. There we go. And that's the same thing as 21 over 99. Or, if I want to reduce it more, 7 over 33. So 0.21 repeating is the same thing as 7 over 33. All right, folks. Why don't you guys go ahead, and as you guys practice that a little bit, we'll talk more about it tomorrow morning. All right, take care.